Hello, everybody. This is Mr. Winchell here. I just wanted to record the day's lesson for today. This is specifically for alphabet letter A through K. I apologize for not having class today. Hopefully, you guys saw my email I sent you. I am a golf coach, and I had to go to a Whippeals tournament today. I was not notified of this until like Thursday evening, so I was not able to tell you guys in class last week. I'm sorry about that. All I wanted you guys to do was to finish the atomic structure packet yesterday, which is, Monday, which is actually today I'm recording this, and that's due today, Monday, so please turn that in if you have not yet. I also wanted to remind you guys that I told you every other week we're going to try to do a vocab quiz. So this week we're going to do a vocab number 2 quiz, and I need you guys to take the quiz by Friday. On the screen, you guys can see the 15 words for this week and the 15 definitions. Just a reminder, all 15 of these words and definitions are in the vocab folder on Schoology. Please study the 15 words and what they mean, and then when you guys are ready, please take the matching quiz on Schoology before the end of day Friday. Today, I want you guys to take a little bit of notes, so please open up your unit number 2, part 1 notes. I'm going to go through these faster than normal. Since you guys are at home just watching a video, you guys can pause this and rewind it. Go as fast as you want. The PowerPoint is also on Schoology and Google Classroom if you would like to view it there. Okay, so today I want to just talk about some chemical bond concepts. There are 2 major types of chemical bonds, ionic bonds and covalent bonds. Okay, they are different types of bonds. I'm going to briefly go through them. I'm going to spend most of my time on number 2 because that is the main type of chemical bond that occurs in living organisms. Okay, ionic bonds. Ionic bonds are formed when you have a metal and a non-metal forming a chemical bond, and they take those electrons that we talked about last week called valence electrons, and they transfer them from one atom, specifically the metal, to another atom, specifically the non-metal. Now, because in this case, one of the elements is gaining an electron, one of them is losing an electron, remember, electrons have a charge. Because the number of electrons is changing, each of the atoms gains a total charge. One of them becomes positive, which in this case becomes the metal, and one of them becomes negative, and that one's the non-metal. So the 2 of them become what are called ions. Okay, let's look at an example below using Bohr models, which I showed you guys how to draw last week. If you look at the sodium atom, it has 1 electron on its third outer ring. Chlorine on its third outer ring has 7. You guys remember I told you the magic number was 8. Chlorine wants 1 more electron to fill out its outer shell, and sodium actually wants to get rid of its outer electron. Look what happens on the right-hand side when sodium transfers its 1 electron to the chlorine. Both of them end up with a full outer shell with 8 electrons. And in the process, sodium gets a positive charge, chlorine gets a negative charge, and this caused them to become attracted to each other, and that's what an ionic bond is all about. Now, covalent bonds are different. This is when you have 2 nonmetals, and they work together by sharing electrons so that both of them gets a full outer shell. Now, I want you guys to write a definition of covalent bond in your notes. A covalent bond is a force that bonds 2 atoms together by sharing electrons, and the goal is to obtain an octet, which again means 8 electrons in the outer shell. Now, there are exceptions to this. If you guys remember, hydrogen, for example, only wants 2 because that first energy level only holds 2 electrons. But most atoms want 8. Okay, so co means together. It's 2 atoms working together. Now, when 2 atoms share a pair of electrons, it forms a single covalent bond. So if you look at the picture below, you see 2 fluorine atoms. Each of them has 7 dots or 7 valence electrons around themselves. They're each missing 1 electron. So what they do is that they each take those 2 single electrons that they each have, each one of them has 1, and look on the right-hand side, you'll see that they're both sharing those 2 electrons. That is called a covalent bond. Okay, now I said this earlier, this only occurs between nonmetals. I'm not going to go into the reasons for this, but basically nonmetals have one or two missing electrons. They need one or two more. So in order for two nonmetals to make a bond, they each have to share them because neither one wants to give them up. Now, there's a couple different types of covalent bonds. Okay, so let's look at water first. Water forms single covalent bonds. If you guys look at the model on the screen, you'll see that there's three atoms there. The hydrogens are the one on the right and the bottom. They're each sharing two electrons with the bigger atom, which is oxygen. So only two electrons are being shared. That's called a single bond. Okay, now let's look at carbon dioxide. Carbon dioxide has two what are called double bonds. If you look at each case where the arrows are pointing, there are four electrons being shared. So each pair, which is two, is a single bond. Since they're sharing four, that's a double bond. Okay, and then let's look at one last example. This one's a lot more rare. We're not going to really see any examples of this year except for this one right here. Nitrogen gas forms what's called a triple bond. 6 electrons are being shared, but the whole goal, if you look at each one of the three examples I gave you, count how many electrons the atoms have, and it will always be a full shell, which is usually 8, except for in hydrogen's case and water is only 2. Now, when two atoms form a covalent bond with each other, they create what's called a molecule. Okay, so molecules are specifically held together by covalent bonds. Now, remember, this is the major type of bond we're going to spend our time talking about because almost every compound in your body is a molecule, meaning it's held together by covalent bonds, like water, fats, sugars, DNA, proteins, and so on. Now, sometimes two molecules can get close to each other and form what's called an intermolecular attraction or intermolecular force. Okay, so there's a difference between inter and intra. If you ever see an intra word, it means within that object, like intracellular means within a single cell. Intercellular means between two cells. So sometimes two molecules interact with each other, not by forming a real bond like covalent or ionic, but just due to the fact that they have slight charges within the molecule. And we're going to talk about examples of this later on, specifically dealing with water. I usually show you guys a video right now about geckos and how they can walk up walls, which deals with intermolecular forces. If you guys would like to watch that video, I encourage it. I'm not going to show it during this video, though. Okay, now, sometimes covalent bonds where the electrons are being shared, they don't share the electrons evenly between the two atoms involved. When they share the electrons unevenly, this is called a polar covalent bond. Okay, polar, think of a magnet. Magnets have poles, a positive pole and a negative pole. So some magnets are like that as well. If you look at the molecule below, you see the right-hand side has that weird little D-looking symbol that's called a delta, and there's a little negative next to it, a temporary negative charge. And if you look at the left-hand side, it has a temporary positive charge. And the reason is the bromine on the right is pulling the electrons towards itself more strongly. Okay, because bromine in this specific case is pulling electrons more strongly, causes a slight negative charge to appear on that end of the molecule because electrons are negative. So because it's pulling the electrons stronger, more electrons are moving over there, it becomes slightly negative. And the reason bromine pulls on the electrons stronger than the hydrogen is that it is a bigger atom. It has more protons, which are positive. And remember, positive protons are attracted to negative electrons. Now, when you have what's called a polar molecule, the two ends, the two charges are called dipoles. Di meaning two. Two poles like a magnet, a positive end and a negative end. Okay, water is an example of a polar molecule, and this is why we're talking about this. Water it has a lot of special properties, and they're all or almost all due to this fact right here. Oxygen has more protons than hydrogen does. So oxygen pulls the electrons in the covalent bond more strongly than the hydrogens do. So the electrons move closer to the oxygen, and the oxygen end of the molecule becomes slightly negatively charged. The two hydrogen atoms become slightly positive because the electrons are moving away from them. I'm going to come back to that fact that water is polar in another lesson. The last thing we'll talk about today is just a chemical reaction and the parts of it. A chemical reaction is when you take one set of molecules or chemicals and you change them in some way into another set of chemicals or molecules. The point is their identity is actually changing, not just their appearance, the actual chemical identity of the substance has to change. Now, if you guys were in class right now, I'd be doing some demonstrations for you. I'm not going to do that in this video, but if you look below, fire is an example of a chemical reaction, or the one on the bottom right, they're taking sugar and you put sulfuric acid in it and basically looks like a black snake. If you guys know what that is, it's a type of firework, but it's a chemical reaction example. Now, there's two halves to a chemical reaction. There are the reactants and there are the products. The reactants are the ones that are written on the left-hand side of the arrow. They are the substances that enter into the chemical reaction. They're the ones that react together. That's why they're called reactants. Now, the other side of the chemical equation has the products. The products are the things that are formed during the chemical reaction. So, for example, if you, in that picture on below, it shows a propane gas burning an oxygen. So the propane, the oxygen, the reactants on the left-hand side, and the products, the things that are formed out of the fire, comes carbon dioxide gas, water gas, or water vapor, and heat. So those are the products. They go on the right-hand side. Now, in order for a chemical reaction to occur, you always have chemical bonds being broken and new ones being formed. So chemical bonds breaking, new ones forming. Okay, so that's why it's a change in identity, because the molecules are actually breaking apart and forming into new molecules. So it's not just a change in appearance, it's a change in the actual identity of the substances. Now, last year in Science 9, you guys probably talked about potential energy. Potential energy is stored energy, basically. You guys last year probably talked about kinetic energy and potential energy. Potential energy was like pushing a spring down or lifting something into the air, which is called gravitational potential energy. But there's a different type, and we call it chemical potential energy. Okay, so chemical bonds are a form of potential energy. There's energy stored within the chemical bond. Now, this is key to your understanding of basic chemistry and how life works. Whenever chemical bonds are broken, the energy stored within those chemical bonds is released. And this is basically how your food provides your body with energy. Your body takes your food, it breaks the chemical bonds, it releases that energy, and it harnesses that energy so that you can stay alive. Okay, so this is also why when you take a piece of wood or paper and you set it on fire, it releases heat and light. Where do you think all that energy is coming from? It's coming from the molecules themselves. When you take the wood and you burn it, you're breaking trillions and trillions of chemical bonds, and that energy all gets released very, very quickly, and it creates a lot of heat and light and sound. Now, what happens to the wood? The wood doesn't just disappear, it's being turned from wood into carbon dioxide gas and water vapor, which goes in the atmosphere. So it's not just disappearing, chemical bonds are breaking and new ones are being formed. Now, in order to start most chemical reactions, you require a little bit of energy input. Okay, so chemical reactions generally don't just start on their own. Okay, so you need to put some form of energy into it to get it started. Again, I normally show a video right here. I'm going to skip it just for this video. If you would like to watch it, the link is right there. Now, the energy that you need to add in to get a reaction started is called the activation energy. Pretend you're the man below. You want to push that boulder from spot A to spot B. You can push it there, but to get it down the hill, you have to first push up that little hill. So you have to put a little bit of energy in to get it to the top of the hill, but think about what happens once you get to the top of the hill. It's going to go down that other bigger hill all on its own. So it takes a little bit of energy input, but in the end, it's going to release more energy after you get it to the top of that hill. So the amount, that hill, the first hill, is called activation energy. Okay, so think of a fire. Think if you want to start a bonfire tonight in your backyard. Okay, the fire doesn't just start on its own. You generally need to put in a little bit of input of energy into it, like a spark. And then once you light the wood on fire, think about it. The wood generally catches on fire, and that reaction happens until the fuel is gone. Okay, so you put a little bit of energy in to get a much larger output of energy overall. And this is going to be a key concept that we're going to come back to later in the year, specifically when we get to your food digesting and the use of enzymes in your body. I normally give you an example of something, hydrogen peroxide, and how it works to disinfect and kill bacteria. And I usually do a chemical reaction example for you guys in class. But again, I'm going to skip that just because of this video and you guys are at home right now. Okay, now, there are things in your body called catalysts, and these are also called enzymes that their entire job is pretty much to just speed up chemical reactions. And how do they speed up chemical reactions? They do this by reducing the size of that hill, that activation energy that I was talking about on the last couple slides. Okay, so enzymes speed up chemical reactions so that your body can do things quickly. Chemical reactions will speed up and it allows you to stay alive. If you didn't have these enzymes, the chemical reactions in your body would go so slow, you wouldn't be able to harness the energy from the chemical reactions and you would die. We're going to do a whole unit on enzymes, so don't worry, I'm going to come back to this concept later on. Okay, so imagine that was the original hill right there, like the guy pushing the boulder up the hill. He's trying to get it down to the product on the bottom of the hill. Now imagine you put into an enzyme into this example. It would be like taking that initial first hill and making it smaller. All it does is it means it takes a little bit less activation energy to get the reaction started, so the reaction will proceed faster because it takes less energy to get over that hill. That's basically what an enzyme does. And we'll talk exactly about how it does this later in the year. Okay, at this point, we're done with the first section in Unit 2, Part 1. I'd like you guys to answer the review questions in the note packet using complete sentences. The answers are all in the note packet. You can find the answers in there. I will collect the entire note packet at the end of the unit. Do not turn it in yet. Wait until we are completely done with the Unit 2, Part 1. If you guys have any questions, you guys can ask me tomorrow in class.